Hello and hi. Today, me and my friends will present our project. But before that, let me introduce about our group members. My name is Muhammad Shafiq bin Sheikh Izzuddin. My other two members' name is Kui Chuang Yi and Wong Kai Yang. We are from SEMM 3033 Finite Element Method Section 2. Our project is about doing an analysis by applying finite element analysis to the ladder frame. So we go to the background study. As we know, ladder is a structure for climbing up or down that consists essentially of two long side piece joined at interval by cross piece on which one may step. Ladder are usually built from wood, fiberglass and metal, which is aluminium. The environment of the work site is the first factor in choosing the material from which suitable ladder is constructed. As an example, if we are doing a work site which is near to the electricity, so the aluminium ladder is not suitable. Okay, ladder also can cause injury if the ladder is not in good condition. So we must ensure the ladder is in good condition before it used. Our problem statement: ladder frame use it as a model to analyze by using finite element method. Okay, we have two cases, which is the case 1 ladder frame in horizontal bending test, and then the case 2 slanted ladder bending test. Ladder frame are made from aluminum 1060 alloy. Okay, so our objective is to apply finite element analysis on the ladder frame and then to observe the different load cases on the ladder frame and to determine the most critical loading case between of these two cases. Okay, we proceed to the Koi Chuang Yi.
Okay, hi, my name is Kui Chong Yin and I'm going to present the log case 1 which is the horizontal bending on the ladder beam. So in this case, we assume that firefighters or with 80 kilogram is maybe it having the oxygen tanks and other equipment, it want to cross this ladder which is put horizontally between two buildings during the fire disaster lah. So we assume that the body weight is going to focus on the both beam on the ladder. Yeah, because we normally we will focus our focus is on the beam because the rocks in the middle is quite we are afraid of putting our weight and anything on the rocks lah. So we assume that the body is going to focus on the beam there. So and for the boundary conditions, we will use the fixed end boundary condition instead of the simply support, which because from the simulation we can see that for the simply support actually it give a very high stress and the support there. So it will make our simulation not logic lah. So it give a result very high stress at this point. So we will use the fixed end. So after we have the point and also boundary conditions, we're going to have the mesh convergence study. So we adjust the mesh element size to to have a almost similar knot value and element value for maximum von Mises. Which for this case we will use the mesh element size of 9 mm because it give the almost similar the knot value and element value lah. Okay, so this is the result of simulation. And we can see that the von Mises stress, the maximum stress is going to act on the middle point, which is near the point we put the body weight. And also the displacement is going to maximum at the middle point because it fixed both fixed end. So if the load is acting on the middle, so the middle will have a maximum displacement. And also for the safety factor, the minimum safety factor for the whole structure of the ladder is 3.5, which means that this ladder is safe when 80 kilogram of people is trying to across this ladder. So after we have the result of simulation, we need to know the accuracy. So this is the calculation, the formulas and also the diagram for the beam, which have a both fixed end. So from this is the tabulation of the calculation and also the simulation result. And we can see that for the maximum one measure, it actually give around 30% of error. However, for the maximum displacement, it actually give very accurate result. And the reason of maximum one measure is difference between in the calculation. We didn't include the shear stress, and we assume that we only view from for the 1D beam only, and so it will give a lower value of this Mohr-Messier stress. So we can conclude that this simulation on this load case is quite accurate and also is quite logic, and it can be the reference for any simulation for the ladder. Okay, thank you. So I will my pass to my teammate for the load case 2. Thank you.
Hi, I am Wong Kayang from Section 2 Group 12. I will presenting the load case 2, which is the force applied on slanted ladder in our project. So as you can see from this picture, this is the slanted ladder. So why we choose slanted ladder is because we rarely see someone we climb the ladder when the ladder is very straight. So for boundary condition, the load applied we assume is a uniform distributed load, which is the weight from a person who climbing the ladder. And we assume that the surface contact with the wall here and the floor here is fixed. So when calculate the uniform distributed load is the mg over L, which the mass times the gravity acceleration over the length of the beam of every step of the ladder. So we can get the 1206.9490 Newton per meter. So before we start the simulation, we do the actual calculation or actual analysis first. This is uh, the most critical part is the beam of the step of a ladder. So this can be represented by this figure. So from this figure, we know that the most critical or the highest moment can be obtained is the M1, M2 and M3. But from the formula here, we know that the highest moment is at both M2 and M3 here, which is the negative 16.6116 Newton meter. So this is the most critical part and the highest stress may occur. So this is the formula for finding the second moment inertia of the beam, and the bending stress is my over I. So we get the maximum bending stress, actual one is 10.325 megapascal. For actual safety factor, we just use the formula yield strength over maximum stress. So we will get 2.67. So after the simulation, this is all the data collected. That is different in the node value and the element value for maximum von Mises stress. And this is the maximum displacement. So from this graph, you can see that the for both node value and element value of maximum von Mises stress, the value is fluctuating when the element size increases. And generally, the node value is higher than the element value for von Mises stress. While for the maximum displacement, when the element size increases, the maximum displacement decreases. So in this case, we are choosing the smallest element size, which is 10 nm, as our analysis. So this is the figure 2.2.6 is the von Mises stress distribution plot. So we can see that the highest or the maximum von Mises stresses is 8.86 megapascal, and it happens at the end of the beam which is tapped by the person, both end here. It is not very clear, but I can show you it is here and here. So comparing to the maximum stresses we calculated earlier, which is the actual maximum stress, which is the 10.325 megapascal, the error from the simulation is only a 14.19%, while for the maximum displacement, which is shown in the figure 2.2.7, we can see that the highest displacement or deflect is happen in the middle of the beam of the stack of ladder, which is here. The maximum displacement or deflect is 0.184 millimeter. For this, the error from simulation of maximum displacement is 197.7%. It is almost double from the actual displacement. So for the safety factor of from simulation, we use the yield strength divided by the maximum von Mises stresses calculated by the simulation. So we get 3.11, and the error comparing to the actual safety factor is 16.48%. So that's all for my presentation. Then I pass my time to my teammate.
Thank you, Wong Kayang. Okay, so we proceed to our conclusion. Okay, we can conclude that safety factor value for the first case is 3.5 and the second case is 3.11. So, the most critical loading case is a second case, which is the force applied in the middle of the slanted ladder. This is because the safety factor of the second case is lower than the safety factor for the first case. Okay, the result in our finite element analysis for the ladder frame has a little error, which is around 16% to 31% of error for both cases compared to the theoretical. This is because finite element analysis just to be predict, but sometimes the result is not too accurate. However, in this case study, finite element analysis for ladder frame can consider as success due to the both theoretical and finite element analysis shows that the critical loading case is the same, which is the second case. So that's all from our group. Thank you.